So a very, very warm good evening to all the participants here. We have Prabhu sir. So thank you, Prabhu Ramchandran sir, and two of us from the organizing committee. And this time we have all the participants here with us. It's really glad to be here and, uh, in your support and presence. Thank you so much for being a part of this particular program. The intention throughout has been to introduce to you some nice technologies that will be marking our future. And we are trying our best to provide you with the best material and resources. Today, we are lucky to have as our resource person, Professor Prabhu Ramchandran ji. He is a faculty member at the Department of Aerospace Engineering, IIT Bombay. His research interests include particle methods for computational fluid dynamics, scientific computing, parallel and high performance computing, and applied scientific data visualization. He has been actively involved in the FOSS and Python communities for the past 2 decades. He is an active member of the SciPy community and develops many Python-based open source packages that are useful in the context of scientific computing. He is the creator of the Mayavi Python package for 3D visualization. He is a PI of the FOSSI project, through which he has led the development of tools and materials to spread the adoption of Python. He has been nominated Fellow of the Python Software Foundation since 2010. He was awarded the Kenneth Gonsalves Award by the Python Software Society of India and PSF in 2014. He has a lot of accolades in his name, and he is a promoter of open source softwares and tools. We are lucky to have you with us, sir, today. And for us, he will be taking a session on Python for HPC research and education. So without further ado, it's over to you, sir.
Thank you, Professor Bhavya and Professor Sahil for setting this up. Thank you for the kind introduction and setting this opportunity up. It's really nice to have, I guess, currently about 70 plus participants. I'm hoping that the number will increase as we go along. It's nice to have so many people in this difficult time joining in to learn something useful. So at the outset, I'd like to say hello, everyone. Welcome. And I hope this session is of some use to you because it's a very general audience. It's kind of difficult to prepare exactly what will please everyone, but I'm hoping there's something in this for everyone. And I've titled my talk provisionally as Python for HPC, which is short for high performance computing, research and education, in the hope that at least one of these areas would be something of interest to all. So I'm Prabhu, and I actually am a co-PI for this FOSSI project, and I work out of the aerospace engineering department. My primary areas of research are all very technical in aerospace engineering, but they broadly revolve around scientific. I stay at the IIT Bombay campus. It's a lovely campus. As you can see, this is a picture of our campus. This is a picture from the hill that's on campus. And this is the Powai Lake. And this is actually our campus. So it's a lovely little campus that's in Bombay, but yet kind of ecosystem of its own. So I'm privileged to be part of this campus of IIT Bombay. I'm really grateful to this to IIT for facilitating a lot of the work that I've been able to do. So I'd like to acknowledge their support. So broadly, what I tend to work on is computational fluid dynamics. Basically, what we try to do is use computers to simulate fluid flow or solid mechanics kind of problems. And these are intrinsically very hard problems to solve. They are not at all easy to simulate. So typical simulations can range anywhere between a few minutes to many days to even a month, right? So these kind of simulations are performed, and doing these requires a fair bit of work. I also teach in an aerospace engineering department, so I have to teach some courses regarding that. But on the side, I've always been developing a lot of open source packages. So one package for which a lot of people have used this package is called Mayavi. This is a 3D visualization tool that was written entirely in Python. It was written about more than 20 years ago. So it's for many years it's been under development and growing. But of course, recently I've not had too much time to actually spend here because I'm also a full-time faculty. But it's a popular package that a fair number of people use. So I've been lucky to be able to create these kind of packages. There have been associated with this package, there are several other packages as well, which I've been heavily involved with as well. So I've had the opportunity to work in a variety of open source projects. So apart from Mayavi itself, there's another set of projects that I'm going to actually talk to you about today. These all are centered around some of the research that I'm doing right now. And I'll talk to you more about these as we go along. One of these is PySPX, the other is called Compile. There's something else called Automan. And then there's an online testing and learning platform as well. And then there are other tools as well, like extracting and annotating media kind of tool that I've been involved with. So there are a lot of these open source projects, but I'm not going to talk on all of them today. I've also been very fortunate to be associated with this FOSSEE project. Many of you have already heard from Professor Kannan Odgulya, who gave a talk at the same occasion a few days ago, I believe. In fact, I checked his talk out online, and he has actually covered in great detail a lot of the aspects that the FOSSEE project do, and also about spoken tutorial. So I'm not going to talk about any of the topics that he touched upon, but he did not talk about the Python project too much. So I will talk a little bit about that as well. So I'm going to split my talk into two parts. I'll try to finish this in about 45 minutes. Professor Bhavya, is it okay if I take up to 4:55? Because I think I started at about 4:10.
Sure, sir, sure.
All right, okay. And then we'll have 15 minutes for Q&A. All right, so the outline of my talk is basically going to be as follows. I'm going to talk about how Python facilitates my research. So rather than giving you in an hour or 45 minutes, it's very hard to pick a specific technical topic and dive into the details. I want to sort of show you breadth. Okay, I want to show you how Python has actually facilitated my own personal research. So I will pick up various pieces from my research, current research interests, and sort of show you, the sort of line that passes through these in terms of Python. And then I will wrap up with some Python-based FOSSEE resources that you will be able to use. Hopefully, you'll be able to make use of these. And all of the things I'm going to talk about are largely open source projects. Okay, so they're available under a very liberal BSD kind of license, so which means you can use them for your own work as well. So I'm hoping that these will be useful. All right. So let's move on to what I want to communicate. The first is how Python facilitates my research. And in this, I'm basically going to break it up into three aspects. The first is my primary work is centered around numerical methods for partial differential equations. So PDEs is short of partial differential equations. And I'm not going to get into any of the mathematics here. I'm going to mostly focus on the scientific computing angles. So it's more of pictures and things like that. I'm not going to get into the gory math at this point. Now, because of the nature of the work, numerical methods for PDEs requires high performance computing. I'm going to talk about the kind of tools that are available that allow us to do high performance computing. And some of these tools are tools that we have built. So I'm going to talk about those. And finally, I'm going to talk about a very important aspect that is often overlooked in numerical computing, especially, is the fact that a lot of research is not reproducible, which means people do not spend enough time making the tools easy or making the results easy for other people to verify. So I'll talk a little bit about this as well. So I'm hoping some of these things will be useful for a lot of people. So the first question most people would have at this point is, why Python, right? So why did you pick Python of all languages? It's firstly, it's an old language. It's not like one of the new kids on the block, but that's also its strength, that it's an old language. So it's been well established. It turns out that it's a very general purpose language. So it's not just tailored for scientific computing or for websites or for ML/AI. It's very general. So you can do all kinds of things with Python. It's very easy to learn and use. So a lot of students, for example, find it very easy to learn this programming language. And some introductory courses that I teach, I actually teach them Python along with that course. The other great thing about it is it has great support for scientific. which means if you're interested in doing any kind of numerical computation, Python has excellent support. And the biggest aspect is the fact that it has a ton of libraries. So if you're looking for any kind of thing you want to do in Python, there'll probably be a library that already does it. So this is a very, very useful and important aspect about Python. So let's just quickly, look at the kind of things you can do. So one really nice thing, supposing you're doing any kind of data analysis. So this is true even if you're looking at, if you're a data analyst or if you're a scientist or a researcher, right? The thing is, you often have data, and it's not always clear that you know exactly the algorithms and the nature of the algorithms to apply to a specific data set. So what you really need is an environment where you can write code, play with the data, and actually make visualizations of that data. So here's a very simple example of starting up a little IPython session and typing out some code and actually looking at the results. So this is extremely useful because this is how everything begins. It all starts here, as you all know. Now, one part of this is numerical computing, which is here it's computing some Bessel functions. Here, the other aspect is also sometimes you want to do symbolic computing. So if you have like a symbolic expression and you want to take the derivatives of the symbolic expression, this is very useful for a lot of things, right? So even if you're trying to understand some new machine learning algorithm and you have an expression that you need to differentiate, for example, it's very convenient to be able to have a symbolic engine. And there are tools like SymPy, which is a Python-based package for doing symbolic computing. And then you can also do very more fancy things like 3D plots, interactive three-dimensional plots. All of these can be done from the comfort of Python. So this is like a very, very important use case for Python. But then it's not just this. It's not as if you just do things like, for example, there are special purposes programming languages like say MATLAB or R. They're all very data centric. They are not geared towards building a general purpose application. But with Python, you can actually build a full-fledged application. And this is a full Mayavi visualization, which allows you to do a variety of 3D visualizations, but in the framework of an application. And this is also built with Python. Now, all of you probably already know this. Jupyter notebooks are built using Python. They're extremely powerful. And they allow you to embed a mixture of code along with text, mathematics, and the results in a very nice, friendly web-based environment. So Jupyter notebooks are also first, they came out in the Python universe, and then only other languages started getting added. So again, this shows you the power of Python, the fact that you can actually build these kind of things using Python. So that's the general story. So how does it play a role in our research? So in my work, we basically use Python as a high-level language. But it turns out that Python is also very good to describe your particular algorithms or the problems that you're interested in at a very high level, and also be able to generate low level. So as a result, what we have found is because Python is easy for users to use and students to pick up and start doing things usefully, we find that if you allow them to write high level code that describes a specific problem, and then use that high level description to generate low level code that can actually run extremely fast, that's an extremely useful approach. So what we do is we allow people to write things at a high level in Python, which allows us to construct fairly sophisticated kind of applications with the kind of richness that Python affords. And then under the covers, we generate high performance code. And to do this, we have actually introduced a few interesting packages. The first is called Compile, which is actually a package that came out of this package called PySPH. So what it does is it allows you to write parallel algorithms. And I'll talk about this in a little while in pure Python. You write these pure Python parallel algorithms, and it can actually execute either on a single CPU or on a multi-core CPU or on a GPU. And based on this, we've also built a package called PySPH, which is a package that allows you to do particle methods. And I'll talk about this as well. And then to distribute these computations across multiple machines, we use a package called Zoltan, and we have a wrapper to that called PyZoltan. And finally, to actually make automated reproducible research, we introduce the notion of automation so that you can actually automate an entire publication using another tool called Automan, which again is developed in our lab. And all of these are produced with a BSD license, so you can feel free to use them. And I'll talk about them a little more. Now, many of you will probably be wondering, well, why not C++, C++, or Fortran? The problem is these are not too agile as programming. So even though C++ has improved a lot, it's a very complex language. And it is not easy to do interactive exploration. And even though Cling exists, and I'm aware of that you can do a Jupyter Cling-based interactivity, it's not the same as Python. And very often simple things take way too much effort. And finally, it's very hard for us to pick an undergrad student, for example, and have the undergrad student do something meaningful quickly using a difficult program. They are much more proficient at doing something using something like Python. So this is a very important motivating factor. So I'm going to jump right into compile and just walk you through some simple applications. Don't panic at this. This is basically a simple example of a collection of particles that are going to interact via Lennard-Jones potentials. I'm not going to show you any animations here. I'm just going to give you a high-level idea. So imagine that you have, say, 10,000 molecules. Each of these molecules essentially interacts with other molecules using a potential, right? And this is the potential function. And if you differentiate that, you get a force. So if I give a particle I and a particle j, the force of the particle j on the particle I can be given by this expression. Okay? So now if I have n of these, it's an n-body problem, which means n of these interact, and you can you'd like to be able to solve the interaction of these particles. So if I want to now run this, I have these n particles, and I want to be able to run this problem very efficiently on, say, a GPU or even a CPU, I'd like to be able to write this code once in Python, ideally, and be able to extract maximum performance from either my laptop's CPUs, multiple CPUs, or on a GPU. Okay? And I don't want to make changes to my code. So compile is built around this basic idea. The idea is that you write your code as pure Python. So this is all pure Python. There's no low-level programming language here. Okay? So it's just a simple function. You give it a small decorator which allows you to annotate it, and essentially it will do jitting for you, and it will generate low-level code, compile that, and allow you to execute. But this function here, all it's doing is it's computing the force, this same force that I talked to you in the previous slide, this force, it's just computing that pairwise. So it's saying for all other particles, find the contribution of their force, it just is writing out that force and adding it to an array over. That's all it's doing. Now, once we have this, we can basically say, all right, let's use all the cores on my laptop. I can say use OpenMP, create the initialization, which is all the particles. In this case, I'm doing two-dimensional interactions. So I have like 10,000 particles. So I'll just put a dot, dot, dot here. I'm not filled in the details, but you can imagine. So if I want a grid of particles, I can just create a grid of particles. And then I can simply say, okay, call this as an element-wise kernel. I can just say, look, invoke that function, but do it completely in parallel. The great thing is, if I just do this and run it, it will actually execute this on my CPU and use all of my CPU capabilities. But the nice thing is, if I want to say I want to run the same code on a GPU, I don't have to do anything. I just have to say use this config instead of using OpenMP, use OpenCL or use CUDA. And then it'll ask my right device and it'll actually execute the same exact code on the GPU. So this is really nice because for a 4-core machine like the one I'm running this on, these are kind of quick results for that particular computation. If I increase the number of particles, you basically see that it's actually exceeding 5, which means it's actually scaling really well on this on my current hardware. Okay, I have only 4 cores, so it's basically extracting as much power as possible in this case. But then I can run the same code on a P100 GPU, and it turns out that again I can get excellent scale up. So this is a speed up compared to a single core on my single core. Okay, this is a P100 GPU, and you can see that whether I run it on OpenCL or CUDA, I can get close to a 175 scale up with the same exact code. So this is the power of being able to do something like compile. The advantage is I can write code at a very high level in pure Python, and then we do sophisticated analysis. We look at that code, transpile it, and then execute it on a GPU, for example. Now that was a toy example. We actually have if you look at the documentation for compile, you'll see that we have a small example where we've compared this with a established software, which does molecular dynamic simulations for the same problem. And we are neck to neck, as in we are actually a little faster than them. But obviously, if you have a software that's more sophisticated, they probably do other things that we're not doing. But you can very clearly see that our performance is really good. So the nice thing I'm trying to talk about here is that given the power of Python and the fact that it has all of these powerful libraries, it's possible for someone like me, an aerospace engineer, to basically put things together in a very powerful way, where I can have people writing code at a very high level and still extract very powerful performance. So this is one example. The second example I'm going to look at is PySPH, the package itself. PySPH is basically a package that allows you to do what's called smooth particle hydrodynamics. It's a numerical technique that allows you to simulate a variety of different challenging problems. I'm not going to get into the gory details of that, but I'm going to just show you some examples of the kind of problems that you can solve. This is also an open source package, and you can read the documentation for it online. It's posted on GitHub as is compiled. Both of them are posted there. And again, the same idea is used here. Users will write code in pure Python at a very high level, kind of like the code that we showed for the compile example. And from that high level Python, it auto generates high performance code, either C, C++, or something for use on a CUDA enabled or an OpenCL enabled GPU. So it basically supports multi-core GPU execution as well as some NPI based parallelization for distributed. And it's cross-platform, so it will work on Windows, Linux, and Mac OS X. So it's a very powerful package, and it also features another nice useful thing. So as I told you earlier, Mayavi is this 3D visualization package. So when it comes to SPH, it's a particle-based simulation. So it turned out that when you're doing any kind of simulation of this kind, it's very important that you're able to visualize the results. And you want the results, the visualization tool to be kind of tied to your particular problem. So because of, again, the fact that Mayavi is implemented in Python, it's possible for someone to actually create a UI like this. So this is a UI that I built, which essentially is a very customized version of Mayavi, if you will, which allows you to inspect a set of files. So it gives you a very rich user interface. This is a full 3D window to interact with. And then you can animate it, you can generate movies from this, you can look at different properties and things like that. And again, the key idea is this. It's not like I'm a software developer sitting full time and building this. I have bits and pieces of time, just like all of you. I guess most of you are faculty here. So that you don't have a lot of time. You have very little time, but you still want to be able to do productive things. And that's the power of having a very powerful language like that, a high level programming language, because it allows you to do these kind of things as well. So I'll just move on to some nice simulations that we've made using PySPH. So what we have here is this glass tank. This little thing you see here, this box you see there is actually water. And this is imagine this is some kind of a structure that's sitting there saying S, P, and H. It's just a toy. And we're just going to run the animation. So what's happening here is, imagine that this block of water is sitting there. And now when we start the simulation, that water is essentially going to fall, right? This is called a dam break problem. Okay? So I'm going to just run this and you'll see what happens. So the water essentially flows, it hits that, right? And then the water sort of flows. And you can see the waves on the water and all of this stuff. So this is the kind of simulation that these tools facilitate. So I hope you understand this is fairly complex. So this has a free surface. It's doing fluid mechanics equations. It's doing fluid and these rigid body interactions. And the rigid bodies are among themselves colliding. All of this stuff is being captured. And all of this is captured using particles. And the high level is all written in pure Python. So here's another problem where we are going to just focus on this and look at the free surface. So the free surface is the surface of this water. And if you look at this, so essentially the water is going to flow, hit the walls, and then flow back. You kind of see the waves. So it kind of looks like a wave that you see. But this is a simulation that's generated with PySPH. And then we do ray trace rendering using PogRay to generate these kind of pretty looking images. So this is the kind of thing that we can simulate. But it's not just fluids. We can also do structures. So here are two steel rings that are essentially colliding and then going back. So you can see these kind of simulations are also possible using SPH. So the reason I got into SPH was simply because it's very versatile and that we can do these kind of simulations very easily. And recently, in fact, just a week ago, we just submitted a publication where we're looking at this aspect of computation called adaptive particle resolution. So what we have here is we have flow from the left to the right. So it's like a cylinder placed in a mass of fluid which is moving from left to right. It's a very classic problem. And what you have here is the particles, as you see here, they are very sparse here. These dots you see here are particles. As you move closer to the cylinder, you can see that it starts getting more and more dense. Right? So this is also done with SPH, and it turns out that this is a non-trivial computation. It's very hard to do these kind of computations in SPH. So what you're going to see here is the flow is going to evolve, and what we're plotting here is what's called the vorticity. So the vorticity basically tells you how things are spinning. So if it's blue, it's spinning like this. The fluid is spinning like this. If it's red, it's spinning the anti-clockwise size. Okay? So let's just see what happens. This is flow past this, and you'll see that essentially two vortices form behind the cylinder. So one is turning this way, the other is turning the other way. And now what you're going to see is, notice that the refinement of the regions is essentially growing as you move away. So wherever there's something interesting happening, the algorithm automatically adapts and refines those regions. So as you can see here, there's like it was originally very sparse, but towards the end, you'll see that it actually is much more refined. So this is called adaptive particle resolution. These kind of simulations are now possible. Again, these are all implemented purely in Python. We don't write any low-level code. All the low-level code is generated for us using the tools that we built. So there's a very powerful kind of thing that you can do this. Now, the nice thing is, a lot of the stuff that I've talked to you so far, people will say they're all traditional algorithms. Right? They're all kind of old school. These kind of computational techniques are considered a little old-fashioned today, even though they're extremely important. And the new rage is, as you all know, data analysis, artificial intelligence, and machine learning. But it turns out that because we rely on Python, you all know that Python is like a powerhouse for all of these aspects as well. So data analysis and statistics, for example, there are a whole bunch of these nice libraries that Python provides, like pandas, stats models, PyMC3. So if you're interested in any of these, they're all Python based. Same way, if you want to do machine learning, it's like scikit-learn. And then if you want to do DNNs and things like that, TensorFlow and PyTorch are fantastic. And all of these are Python based, which means all of the skills that one learns in learning this programming language can actually directly pay dividends by just quickly jumping into this area, because these libraries are available and they have a syntax that's the same kind of Python syntax. In fact, PyTorch's syntax is inspired by NumPy. So if you know numerical computing in Python, it's very easy to just quickly jump into something like that, or even TensorFlow. So this is again a very important aspect. And recently, we've also started doing some interesting work with neural networks and partial differential equations. So in fact, we have a recent paper that we just put out on arXiv. You can check it out. It's called SPINN, Sparse Physics-Based and Interpretable Neural Networks. So this is very interesting in the sense that if you look at neural networks applied to machine learning, so this is called scientific machine learning, you'll find that a lot of these methods typically use neural networks like a black box, which means you just treat the neural network as if it's a function approximation, a function approximator. You plug in whatever is your objective function, run through the optimizer, and get a result. So the difficulty here is a lot of these are not interpretable at all, which means you don't really know what's happening inside that. We know that a neural network is a universal approximator, but you don't really know. You have no mechanism to fine-tune what's happening inside. And what we've done in this work is basically show that this we can map this to a very traditional technique, a meshless method. And this allows us to fully interpret a neural network, this kind of a sparse neural network. And they're also sparse, which means the interconnections between these layers are fewer, which allows us to be very efficient and actually make some very interesting computations. So here's a simple simulation. We're looking at what's called an advection problem. Maybe the details are not clear, but I can't explain too fast. Basically, it's a linear advection problem. It's a partial differential equation, and it evolves in space and time. So in space, the initial solution looks like this. It's a Gaussian pulse. Okay, so this is the time axis going in this way, and on this axis is the space axis. And I have a Gaussian pulse. What we're looking at is how does this Gaussian pulse evolve in time? And this wireframe that you see on top here is the solution, the exact solution. So in this case, we know that the exact solution is essentially a translation of that Gaussian pulse. Essentially, the Gaussian pulse here is essentially going to move like this. What we want to see is, can the neural network actually pick this up? And what this simulation is going to show you is each of these dots, this is a profound thing here, is that each of these dots is actually a neuron. It's actually a neuron. And this is something that you will never see in any neural network paper. So that's the new thing that this paper talks about. And you'll see these nodes actually automatically adapt and to capture that solution. So let's just see this. I'm going to run it. And you'll see that these nodes are essentially going to adapt. So they're actually optimizing this solution, and they're going to come very close to the exact solution, as you can see. And notice that all of these are aligned exactly along this. And this is automatically brought out by the neuron. So the power here is we can solve partial differential equations and we can interpret their solution. And this also allows us to do it the other way, which is we can use techniques that we already know in order to tune neural networks. Otherwise, neural networks can be these black boxes. People will say use 5 layers, so many neurons, and you really don't know why they're doing it. Whereas here, there's an actual physical basis on which you can decide about. So this is again research that's very recent, that again is powered with Python. So all of this visualization is made with Maven. The actual simulations were done with PyTorch. And again, it's very easy to dabble into something like this, especially if you have a good command over a programming language like Python. So I've talked about a lot of things. One very important thing that is missed out very often is the aspect of reproducibility. So a lot of people will have published papers, they'll have a lot of very interesting results. But one big problem is that supposing you're given a paper, in fact, this is a good exercise for you to do. Pick a publication, some reputed journal publication. Ask yourself the question, can you reproduce all of the results without the author being present, as in without any communication with the author? You will find that 99.9% of the papers will not be reproduced, which means there's no way you can reproduce that paper without the author sitting next to you. Okay? And even the author may struggle after a few years, right? That's the reality is like that. So it turns out that this is a very important perspective, and it's been looked at in the past. Many people have actually discussed or talked about this. In fact, it's the fundamental basis for all of science. So this is a very beautiful quote, and I'm going to read it out. It's by Buckheat and Donahoe. They're paraphrasing another researcher, Claire Bow, who's done some seminal work in this area of reproducible computing. So an article about computational science in a scientific publication is not the scholarship itself, it is merely advertising of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generated the figures. So this is an aspect that you will very seldom see in publications. So it turns out that in fact reproducibility is pretty bad in the community. Most research papers are not reproducible. In fact, long ago, there was a group in Arizona where they looked at computer science papers. And they found that out of 600 papers that they looked at, only about 220 or so could actually be compiled, let alone reproduced. And this problem is not true just in medicine. It's also true, in computer science, it's also true in medicine. Many medical studies are not reproducible. So there are these problems, very serious problems. And the question then is, well, if you're doing a lot of this, does it make sense to call it science if it's not reproducible? So what we've realized in our group is that we want to make a difference here. So we've built this framework called AutoMap. It's a very simple idea. But the essential thing, what it does is, it lets you generate all the figures for your publication with a single command. Which means, of course, it's not as if it's free. It doesn't happen automatically. You have to sit and write the code for it. But there's a framework that allows you to run and execute multiple simulations and then collate those results and put it so that you can just generate it in one shot. You can think of it as a glorified makefile. Okay? In fact, I ran into this problem. So I was teaching courses and I was writing a paper in which I was the first author, and I needed to run like 70 simulations. And if I were to just run those simulations for a long time, it will take me 5 days to run them. So I realized that I had no mental bandwidth to actually keep track of these 70 simulations. So I actually wrote the framework for that. And what it does is it allows you to run even on idle computers. So if you're on your network, if you have a few idle computers on which you have a login, it can actually run some of your computations on that machine as well. Again, this is written with Python. And it's a tool called AutoMan. And we have a bunch of reproducible papers. So every paper that we published ever since we wrote this framework is essentially fully reproducible, which means you can generate every figure that's been shown in the publication using a single command. So this is something that's very valuable. You can check out the paper. It's all open source. You should check it out. So this may be something that you might find useful for your research. So again, to summarize, why are we talking about Python? First thing is it's super easy to use. There are so many things you can do. As you've seen, the range of applications that I've talked about, all of them are powered with Python. So it's extremely good for high-level scientific computing, and it's also very popular for ML and AI. And the best thing is students actually enjoy using Python rather than a low-level language. So in a sense, I see this as a tool that allows you to bridge the past and the future. Even though I can't say anything about how long it's going to last, but the very fact that I knew Python allowed me to transition from old traditional techniques to more new techniques. So it's a very powerful tool that allows us to so I can think of it as a next generation technology. So moral of the story is there are diverse needs that a researcher has, and that if you learn one language, I would recommend that one language be Python because it's extremely powerful. course, this does require that you master these tools and you master the programming language well. But because it's so applicable, you can do a lot of interesting things with it. So now what I'll do is in the last 10 minutes, I'm going to, or 8 minutes that I have, I'll switch to some resources that we have at FOSSEE that may be useful to you as well. So this part of my talk is essentially something that would not have been possible without the generous funding of the Ministry of Education, which has funded the FOSSEE project for many years now, and as Professor Kannan has already talked to you. So I'm going to just focus on a couple of few things, especially on the Python side. So if you check out the python.fossee.in website, you'll find that it has a lot of information. It's a bit bigger. One part of it is we do free online Python courses. So if you want to learn Python, you can. There are actual self-learning courses available here. There are also Python workshops that we used to do in the past. Now the pandemic has kind of paused this a bit, but we used to actually conduct actively workshops. We have a whole bunch of close to 500 textbook companions that you can feel free to use. They're all freely available. We also have a free online learning platform called Yaksh, which I'll quickly demonstrate if time permits. So as far as the self-learning courses go, these are courses that are designed to be learning by doing. And we have like two offerings. One is like an introduction to scientific computing using Python, which is a 1 day long course. And the other one is a basic programming using Python, which is, it combines the first day of this introduction to scientific computing along with the basics of the programming language, a total of 3 days. And each of these features a lot of programming exercises. In fact, our 3-day course has like 60 plus exercises that the learner is supposed to do online, and then the solutions will be discussed. We also have advanced Python material that's ready, and it's not fully complete, so it's coming soon. And you can check these out here. And these are also hosted on our own learning platform called Yaksh, which I'll talk about. We've also done a whole bunch of these Python workshops free of charge. Right now they're online, but we've not done too many of them right now. And students receive certificates for this. We've trained about 15,000 students in total, not 1,500. And please note that this is not like it's an hour long. 1 day workshop means 8 hours of material. 3-day workshop means 24 hours of lecture material. Okay? So it's a lot. It's a significant amount of online video content. And so effectively, we're talking about 35,000 person days. So we've been able to do a lot of this training using the material that we've generated. And if you're interested in this, you can always write to us at, again, this Python workshops link that's available there. That is available at our python.fossee.in website. There are also Python textbook companions. We used to take proposals for this, but we no longer do. But we have like 500 books. And feel free to check these out. Each of these is in the form, maybe I'll just quickly show you. Each of these is in the form of Jupyter notebooks. So for example, if you look at engineering physics, and just picking something at random, I have no idea how it's going to be. There are like 12 chapters in the book. Each of these is basically a Jupyter notebook. So you can actually, in fact, you can run it. We will allow you to execute it here. You can even edit it. There's some hosting that we provide for that. Or you can, of course, download it and use it on your own computers. The last thing, which is, I'll take 5 minutes to just wrap this up, is I want to talk to you about this Yaksh online teaching learning platform. So as I said, we have these online courses that we offer. The platform that we do this on is developed by FOSSEE, and that platform is actually also implemented in Python. It uses something called Django, and it's an online learning platform. And the nice thing about it is it's designed to do tests and quizzes, especially from the computer science point of view. Okay? So as you all know, learning computer programming is not just a theory. You can't just read a textbook and then say, I know the language, right? You have to practice. So what we do is in this platform, we kind of make these online programming kind of tasks the central theme of these courses. So you can give a student an assignment or a quiz, and you can have them program, and live they will get feedback about that. So it allows you to write these kind of, create these kind of tests, which make it very easy for your students to learn. And the nice thing is you can also monitor quiz progress, which means, let's say you have a student of, you have like 100 students, and you're teaching them some concept, and you know that a few of the students don't get it. So let's say you give them a simple practice exercise, and you ask them all to take it. You can live monitor the students, and you can actually see kind of what answers they're submitted. And if they're not getting it, you can perhaps reach out to them and spend some extra time with the students. So these things are all possible. And recently we also added some additional features given the online context. We've made it easy to add videos and also track the whether your students have watched the videos, at what point have they finished. We also allow people to do in-video quizzes and questions, which is a very good way to create videos. So on top of this, we also support basic math markup and a simple discussion forum. It's not meant to be a replacement for Moodle, but it does offer a much more interactive experience for the learner. And the most important thing is you can do coding tests, programming tests in a bunch of languages. And this entire platform is open source. So we have a hosting that we provide, as in for our own courses and stuff. But the entire the source code for this is fully available, so you can actually self-host if you're interested. And the instructions for this are also available. So what I'll do now is I'll just take you to a quick demo. I have like 3 minutes. I'll take you through a quick demo of the Yaksh platform. I hope the font is visible enough. I'll try to make it as large as I can. So
yeah, it's visible.
Okay, great. Thank you. Yeah. So basically, I'm just going to log in here. You could sign up with Google or Facebook or create a new login. This is going to have a bunch of junk because not junk, but a bunch of courses because I've been using this for many other things. So this is my dashboard. I'm a moderator, and therefore I can create courses. I have a bunch of old courses that I've created. So last year I taught a fluid mechanics course. So maybe I'll just quickly show you that old course. This is the course that we had. These are the course modules. I can add lessons, I can add a quiz, I can add exercises. So I have like a whole bunch of this content here. You can see there's quizzes, there are like videos. So maybe I'll actually show a demonstration later. Let's do that. I'll switch to a student view. And okay, I'll quickly look at this. So this is I was the teacher of this course, so I've not completed the course, but yeah. So if you look at any one of these, if I look at this, so this provides an operational introduction to the course. So it has this video here that I could check out. So I'm going to reduce the font size a bit. So this is a video that I made introducing.
Welcome to A225 Incompressible Fluid Mechanics.
So this was during the pandemic.
I'm Prabhu from Aerospace Engineering.
Right. So I can put up a video here and then add additional material to this if I want. And then I'll show you some place where I've actually added some math markup. This should, I hope, render. Yeah. So here is a summary that we've done a bunch of math and students were very confused. So I wrote out a summary saying, okay, this is how you can do these things. So it supports math markup. It also has a small discussion forum. So someone asks a question and then, I can answer the questions here itself. So it offers a nice way to do that. So let me get back to my, I'll show you a quick demo. My dashboard as a student. I'm going to show you this is a simple course we just created for the purpose of this demo. So here is a simple demo of how it looks as a student. I hope you can all see my screen. So here you have, this is a one single module. It has two things. It has a lesson and it has a demo quiz. Over on the right here, you see table of contents. So what I would do is I would record videos in my course. And then I put them up on YouTube. And then
Welcome back to this session. Let us take on a practical example.
So it's going to keep running. But essentially, I put it on YouTube, give a link to that. It will essentially allow me to embed the video here. I can then put any additional description that I want here. Of course, students can have comments. But the nice thing is I can also attach,
I told you,
table of contents and things like that.
We do this using a least squares fit. What did we have? We had a data.
So for example,
what do we want to do?
I don't know if you're able to hear the audio here.
Equation is essentially of this form. We want
we can hear
some m into L.
Okay. So what I did was I clicked on this problem formulation and it went to that exact point. That's at some 54 seconds. Okay? So I can put table of contents. The other nice thing is, so I'm going to just go to a suitable point.
Before we have to invert A. Obviously, we can't invert it. Why can't we invert A? Because it's not a square matrix. So the only way you can solve this is to use it.
Okay. So now what happened was I have put up a small poll question here. Okay? It says, do you like the topic on basic cyber? So I can say yes or no, and then hit submit here. And then I can continue to watch the video. So you can do either a poll or a quiz, an actual quiz at this point. So you can actually insert content that allows students to revise material. So this is really nice. It's actually a recommended thing to do when you're doing online courses. But this the tool that we have allows us to look at this. So now what I'm going to do is I'm going to switch back to moderator to show you how it looks from the instructor side. So let's go back to this. I look at the manage course. These are the two lessons that we have. And over here, there's the statistics. So I can click on this and look at the video views, which means I can track who has seen and also tells me how much they have seen. Okay. And then it will also allow me to look at what were the submissions on this, right? So I can look at the poll and I can see, I said no. I was the only guy who said no here. Okay. So you can actually see the statistics of, what was the different students, what did they answer, what was the general impression. So these are very convenient, just in terms of pure instruction, right? Just to teach. But now I'm going to go back again as a student and I'm going to take the quiz. So I want to just quickly demonstrate to you. I'm going to go on to the next and I'm going to take the quiz. So we have a quiz. So I'm going to basically say start. And this basically has a quiz. This is our quiz interface. So you can navigate through all the questions through this navigator here. And then here you basically have the question, which you can basically answer. So I'm just going to randomly select something. This is a multiple choice. And we also do randomization of those choices. And I can say submit this answer. And it moves on to the next question. So for example, considering blah, 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 this is straightforward, right? So I can do, this is a multiple correct choice, which means running out of time. Okay, so I can do multiple choice, multiple correct choice. We can also do programming questions. So here, for example, I can type and let me see if I check the answer, it will basically check. And so now it tells me, look, didn't work. I gave the user input. I expected this, I got this back. I gave you this, I expected this, and I got this back. Okay? So what this allows students to do is they can be given a program, asked to solve it, and then you can get to see how well they're doing this. So basically, this allows us to. I'm just going to close this down. So you can sign up and actually take this yourself. Okay? So let me get back to my talk. All right. So what I'm trying to say is, so Yaksh is this free online platform that we have fully open sourced that's available that can be used for all these kind of rich instruction methodologies. So we strongly suggest that you check it out and feel free to use this in whatever way that works well. So we use this for all of our live courses. Several courses at IIT Bombay use it. Not too many, but definitely some of them. I know I use it a lot. Some colleges outside IIT Bombay use it as well. We tend to use this for our recruitment tests, as well as the spoken tutorial certification tests. They actually use Yaksh. So I'll stop here with a few links to some of these packages that I talked about. Compile, PySPH, Automan. There's python.fossil.in. And Yaksh as well. All of these feel free to check out. Thank you very much for your patience. I'm sorry I took about 5 minutes more. Thank you. I hope this was useful. If you have any questions, please feel free to ask me now.
Thank you so much, Professor Ramchandran. It was indeed a very, very enlightening session. I have been using Python for a long time now, but I think seeing how it can help the visualization task, it can actually make it so interesting and nice, as well as its utility in HPC is completely good. And we'll surely use Python more now. Of course, giving you everything. It has got so many packages. It's a very, very good language to learn. And thank you so much, sir, for giving us your time. To the participants, I know that because of some technical glitches, we could not go live, and there is this restriction of 100. But we have recorded the entire session, and we'll be putting that on the portal. So all of you, all the people who have joined in can definitely get access to it. There are no issues. Now, if
Also,
you
I
have
want
any
to,
queries,
uh,
please feel free to put them in the chat box. We'll pick that
Sure.
up and we'll ask Ramchandranji.
yeah,
Right.
I have one question, Professor Prabhu. So,
Please.
hi,
Yeah, yeah,
this is
please.
within the
Yeah.
site. So, is this Yakshas available on GitHub as well? Like people can
Yes.
contribute?
Yes.
Yeah, he did
Yes.
show the link.
Here it is, github.com/online_test. But it's easier to remember yaksh.readthedocs.io. So you can go there, and I suspect that it will link back to GitHub. All of
And
these
sir,
will.
actually a nice platform. I've been looking for something that can check my codes, you know. I like
Yes.
that demo really.
Right. So it's so we do two things. So in Python, especially because it's Python based, we can actually do. You can even ask people to write a function and then test against that function. So it's very useful. Otherwise, for other languages, you can do like input output kind of test. So I find it very useful when students learn this. It also makes it.
Definitely, sir. Definitely. Okay, so there's one question. It says, what are the Python FOSSEE tools for cryptography?
Oh, excellent question.
Or maybe FOSS tools for cryptography.
Okay. So first thing, I will disclaimer. I don't know anything about cryptography. Right? All I know is there are large primes involved. Okay. So, and it's all about prime number factorization. So that's about the substance of what I know. And I generally use SSH and OpenSSL for all this. I do know that there's bindings for OpenSSL and there's a language a package called Paramicro, but I don't believe that's the question you're asking. So I actually honestly don't know the answer to it, but I'm sure there is something available for it. There's a package called PyCrypto, and I'm sure it does, allow for these things. There's a faculty member called Gajendra Deshpande. He tends to give talks on cryptography using Python, but I don't know if he specifically talks of any particular libraries per se. So
I want to add like there are tools, for example, you can check Open Quantum Safe. This is most on the post quantum side,
Okay.
but there are OpenSSL which you can check for the Python thing. So yeah, there are a lot of libraries for you.
Yeah, so I mean, encryption algorithms you can always write. That's not the difficult part. So I don't know exactly what you're looking for in the cryptography. So it's like
We have one more question for you.
Sorry, yes.
Do these HPC libraries work as in Colab?
On Google Colab? Yeah, of course. Yes. In fact, compile, if you go to our compile page, there's a Google Colab notebook that's available. You can start it up with a GPU and it'll run. Yes. Because it's basically sitting on top of Colab is built on Python. Colab is actually like using under the covers, it's using all these tools. So you can install CUDA, PyCUDA or PyOpenCL and use them. No problem.
And we also hope more contribution from our faculty side on these GitHub profiles. So yeah, I hope so. So
yeah, that would be nice, but it's I know it is difficult because it requires a lot of time and attention. I can understand that it's everybody has very busy schedules. So like I'm privileged in the sense that maybe my teaching load is not as high. But yes, it does take a lot of time. So, but all your contributions, even bug reports, are welcome. Documentation.
I
But
think
I understand that
we are.
my work is niche, so I'm not sure how much translates.
So actually we finished with the time. So if you have more questions, people can directly ask on discussion forum and we can ask from Professor Prabhu.
Sure.
So yeah, thanks Professor. On behalf of this organizing team, OTFF Frost and Teaching Learning Center, Ramanujan College, University of Delhi, we extend our heartfelt thanks to Professor Prabhu for taking our time and interacting with our participants. We really hope to have more engagements with you, sir, in future. Thank you so much for your time, sir.
Thank you very much. Thank you very much.
Thank you so much, Ramchandran, sir. And thanks to all the participants for joining in.
All right. Thank you all. Thank you very much. See you. Have a nice day.
Have a good day.
Bye.